So we'll move forward. Now there are so many of them, so many of the functional groups that we have, functional grouping. So we have acyl halide. Acyl halide. Acyl halide is called acyl because of the alkyl group attached to carbon double bonded to oxygen. Then the halide because there's what? This X here represents a halogen. You've seen them there. The X here represents F, which is fluorine, Cl, chlorine, bromine, and what? Iodine. So this is also a functional group. Then we'll go to alcohols, which we have already discussed. We've seen that's the first example we looked at. And so the OH there gives you the idea. The aldehyde, we've talked about that. Alkyl halide. Alkyl, there's R bonded to carbon, that's the alkyl. Then the X there represents the halide. Then we have alkynes. Alkynes, the functional group in alkynes is the carbon-carbon triple bond. So if it's a carbon bonded to another carbon with a triple bond, then it's qualified to be called an alkyne. It's called an alkyne. Then alkene is carbon-carbon double bond. Carbon-carbon double bond is alkene. And then we have amine. Amine. Amine, we have the nitrogen bonded to an alkyl group. Okay? We have nitrogen bonded to an alkyl group. That is an amine. Then if you have an alkyl group bonded to carbon double bonded to O and then an N, you have the nitrogen attached. That one becomes one, an amide. An amide. And so amide, the functional group in amide is carbon double bonded to O, then CN. That's the one in blue. So all the blues you see represent the functional groups in them. Okay? Then we have the aromatic ring. Any ring that contains a benzene ring in it is aromatic. So this is an aromatic ring. Then so if you have OH representing the R here, it is called phenol. Phenol is a derivative of benzene. Good. Then you have aryl halide. We have carbonyl acids, disulfides, esters, ethers, amines, ketones, nitrites, nitro groups, phosphate esters, thioesters, and then thiols. So these are all form homologous series. So if you take every group, if you take alkenes, they form homologous series. If you take alkynes, they form. If you take carboxylic acid, they form. If you take aldehyde, if you take alcohol, they all form homologous series. And so we continued with the homologous series. I indicated earlier that neighboring members differ from each other by CH2 unit, or that is the fixed mass of 14. Why do we say fixed mass of 14? If you look at the mass of CH2, if you calculate the relative molecular mass of CH2, carbon is 12, hydrogen is 1. Okay? And there are 2 hydrogens, isn't it? So 2 by 1, 2 times the 12, 14. So you see that they differ by each other, from each other by CH2 unit or a fixed mass of 14. That's what it means. Then we move forward. Homologous series can be represented by a general, so members of a homologous series, if we say 2 compounds, organic compounds, belong to the same homologous, or they form what we call homologous series, then it means that those 2 organic compounds would be represented by a general, the same what? General formula. For example, if I say methane and ethane form homologous series, then the implication is that since they are all alkanes, they will conform to general molecular formula CnH2n plus 2, which is the general molecular formula for alkanes. Similarly, if we say ethene and propene form homologous series, then it also says that, or it goes to imply that the 2 organic compounds would also conform to general molecular formula for alkenes, which is what? CnH2n. So that's what I mean by that. The members of the series can be represented by a general molecular formula. For example, as I have already indicated, alkanes will conform to general molecular formula CnH2n plus 2. Then, or CnH2n for alkenes, or just as we have here. And so CnH2n minus 2 for alkynes. Now we have an example here for alkanes. We are going to use the alkanes, the members of the first 10 members of alkanes, to explain homologous series. Now, we'll take the first member. Now, we indicated that alkanes conform to the general molecular formula CnH2n plus 2. Okay? Now, how do we obtain or derive the first member of the alkane group and the subsequent ones from 1 to 10? And that will be able to indicate or clearly show that they conform to the same general molecular formula. Quickly. So, for the number of carbon atoms being 1, which means in CnH2n plus 2, the value of n will be taken as what? 1. So, if you substitute the value of n to be 1 into this formula, we shall obtain this. This is the formula we'll get, CH4. Because C with 1 here is C. Then H2 times 1 plus 2 is what? 4. So you obtain CH4 as a formula. Now, if you have one carbon atom, in this concept, if you have one carbon, we shall refer to that as what? Met. And so the root name will be what? Met, because you have one carbon. Are you getting it? And then we also indicated that the entire concept is about what? Alkanes. And so the ending of the name will end with what? Ane. Just like you have members of the same family having a family name. Okay? Myself, I have a family name, Abba. So every member of my family will have the name Abba attached for identification purposes. That's what functional group does. It helps us in identifying the compounds. And so, in this sense, all the members of the alkane group will end with the 3 letters Ane, A-N-E, so that whoever would see them will know that they belong to the family alkane. And so, for the first one, you have Ane, 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 Ane. So, we notice that the Ane is common for all the members of the series. But for the first member, because the value of n is 1, and when you substitute that, you get only 1 carbon in the formula, it becomes what? Met. So if you combine the met together with the family name, you obtain what we call methane with the formula CH4. Now, the formulas can be put into 2 forms. You have the structure itself and you also have the molecular formula. Okay? Good. Then you come to the second member. For n equals to 2, if you substitute the value of n to be equal to 2 into this formula for alkanes, you obtain CH3, CH3, or you obtain what? C2H6. Okay? You obtain C2H6. And because the value of n is 2, if the carbons are 2, in this sense, we shall refer to that as what? Eth. They will add the usual into this, so it becomes what? Ethane. So the second member is what? Ethane. Then the third member, 3, if its carbons are 3, prop. Then the usual family name, ane, will be added, and that becomes what? Propane. Fourth one, bute. Then you add the family name, ane, butane. Then pentane, hexane, heptane, octane, nonane, and then decane. In that order. In that order. Now, let's now establish why the first 10 members of the alkane group will form homologous series. But significantly, we indicated that for a certain series of organic compounds to form what we call the homologous series, neighboring members must differ by a fixed mass of what? 14, or CH2 unit, or what we call ethylene unit. And so quickly, if you look at this is CH4. The next member is what? C2H6. The next member is C3H8. So between the first and second, what's the difference in carbon? You have 2 carbons, you have 1 carbon here. So if you subtract, how many carbons is left? 1. Then H6 and then H4, if you subtract, H2. So you have, what is the difference between them? CH2. Are you getting it? Then between the third and the second, you do the same. Between HCH3 and CH2, if there's a difference, you get what? CH. Then H8 and then H6, difference is what? CH2. So you see, the difference between this and that is CH2. The difference between this and that is what? CH2. Difference between this and that will also be what? CH2 is common. CH2 is common as you move down. And so for that reason, we say that they conform to the general molecular formula, or they form what we call the homologous series.